Okay, so we were talking about sorts, and we were talking about searches. And one of the things we decided was that, well, I guess what we'd actually gone through is we'd gone through and we were starting on the merge sort, right? We talked about an insertion sort. We showed you how you go through and you move the whole down. You know, you assume that a list of length 1 is sorted. Then you go through and you look at the second element and you take out the second element, leaving a hole in your list, and you move that hole down until that hole represents where that second element ought to go, and then you pop in the second element. And we'll walk through this again a little bit, maybe at the end of class if you guys still have questions. But that was an insertion sort, and what we said was that worst case, at every step, for example, a list that's completely anti-sorted, at every step you have to move that whole n-1 spaces. So for a list of length 0, you have to move that whole, for a list of length 1, you have to move that whole 0 spaces, right? A list of length 1 is always sorted. For a list of length 2, you would have to move it at most 1 space. List of length 3, at most 2 spaces. So you're always putting that hole into the first spot. So on average, that's going to require you, as you go through the entire list, as you get close to the size of the list, the average is going to be you'll have to move that whole n spaces, and you have to move that whole once for every element you ensure is in sorted order, right? So if the list is of length 1, you don't have to move, it's sorted. If it's 2, there's going to be at least 1 step, right? If there's 3, you've got to move 2 elements, 2 steps. If it's 4, you have to move 3 elements. So we decided was there are n, we have to put n things into the correct place, and each time that can take at most n steps, so that's an order of n squared algorithm. And what I promised you was that for a merge sort, that we're going to break that n squared barrier. And the first thing I said we're going to have to do is we're going to have to define what a merge is. And I said if we have 2 ordered lists, 2 lists that are already sorted, we can make one list of twice the size in at most order of n, right? The number of operations proportional to the length of the first list plus the length of the second list. We'll call that total list n, total length n. So, if there are 10 elements in the first list and 10 elements in the second list, we have to go through at most about 20 steps, proportional to 20 steps, to get those into a single list of length 20. And we did that very easily by going through and we look at, they're 2 sorted lists, so we keep track of all the elements we haven't added to our mega double size list yet, right? We start off, we're looking at the first element of both lists at index 0, and then as we put an element into the list, we move that little pointer down so that or that little index down, so we're now, the head of our list becomes farther down until we've completely emptied out one of the lists, at which point we just copy anything left onto the end of our list L. Okay? And you can kind of see that as you go through, at each point, you pull off, at each step through the list, you pull off an element either from L1 or from L2, and you add it on. So you can see that you have to go through this, right, until one of those lists is exhausted, and then you come down here and extend it, and that adds up. So this is this plus this adds up to the length of L1 plus L2. Okay. Anyway, so this is an order of n operation in the length of L1 plus L2. So now let's get down to the merge sort. And the question is, do we want to give the algorithm and then diagram the algorithm, or do we want to diagram the algorithm and then give the algorithm? I think for this time I'm going to err on the side of giving the algorithm first so you know what's coming, and then we'll kind of talk about what it actually means. All right, so the first thing we're going to do is we need to have Well, the first thing we have to do is we have to figure out when we're done. Well, if we have a list of length 1, right, we know that a list of length 1 is always sorted. It has to be, right? There's only one thing in it. There can't be anything out of order, right? You're one thing, you stand alone. And actually, a list of length 0 is sorted. It's just kind of a trivial thing, so there's not really much to do there either. So if the length of our current list is less than or equal to 1 or 0, we're going to return, well, we're just going to return. The list is already sorted. We don't have to do anything else. If that's not the case, then we have to kind of get into something else, right? So this is the something else we're going to get into. Well, we know that a list of length 1 is sorted. So if all of our lists were length 1, we know that we could use a MergeSort to pull them all together. You know, if we had 2 lists of length 1, we could pull them together into one list of length 2 using our merge algorithm up above. So the first thing we're going to do is we're going to make a list of lists. We're going to call that lists of lists, because that seems appropriate. Okay, and what we're going to do is we're going to take our original input, right, our vector v, or our list v, and we're going to convert it into, you know, let's say the length of that is n. We're going to convert that into n lists of length 1, right? Because then we know that all of those individual lists are sorted. So we'll just say for item in v, and I'll come back in and fix that as soon as I get a chance. For item in v, we're just going to do a lists.append item, right? So we're going to lists.append list of item. Right, so now we've taken what's essentially an item of n, one list of n items, and we've turned it into n lists of one item. Okay, so at the end of this, right, if v is 1, 2, 3, 1, 2, 4, 5, why not? It's gonna become 1, 2. Come on. 4. And we're not worried about order here, right? And that should be a pound sign, not a percent sign. Boom. There we go. And now we got to get rid of. There we go. All right, I think that works. Okay, so all that's going to do is it's going to take our list, and it's going to take it from, you know, a list of n items. It's going to make n lists of one item, and we're going to throw those all into a list. And that's the first step. We've actually bottomed out. Right now we know that everything we have is sorted. We just got to put them together again and maintain the sorted capability. So now let's talk about how we put them together again. Well, I kind of gave you a hint that we're going to use this merge we wrote up above. So let's look what this looks like. Well, we're going to go into a list, or into a loop. So we're going to do a while loop. We're going to start off with I equals 0. Right, 0 is going to be referred to the first element of this list's list. So, you know, that's where we're going to start our algorithm. We're going to go through and we're going to process all of these lists together. We're going to end well, let's leave this off for now. While I less than something. I'm just going to put 2 question marks there because I don't know exactly how we're going to end this. We're going to think about this in a minute. And I do know how because I have the cheat sheet in front of me and I've done this a number of times. I'm going to pretend I don't know. We're going to create a new list. Right? And our new list is going to be the result of merging the list at index I with the list at index I plus 1. Right? So we have our merge. Merge returns a new list twice the size or the size of the combined lists we put into it. Right? So we can do our merge, and we're going to merge lists sub 0. I'm sorry, lists sub I and lists sub I minus 1. Plus 1. Right? Is that right? That's right. And now this is a new double length list, and this list has the property that it is also sorted. So if we just throw this on to the end of our lists, then what we have is we have, the first time through, what we'll end up with is, come on, my key stuff is popping up and I can't see what I'm actually looking at, the clue stuff. I should turn the kite. I should turn that off. Okay, so the first time through, we'll take these two lists and we'll merge them together, and we'll append them onto the end of this. Right, let me put this in here. So after one step, we'll have this. Right? So we'll have merged 1 and 2 together. We'll have a double size list. And we can append that double size list onto the end of our original list. And we still maintain the fact that all of our lists, all of these little sublists, are in sorted order. And now we want to jump I by 2, right? Because now we've used up 1 and 2. We want to jump by 2 and use up 4 and 5 at indices 2 and 3, right? So we can say I plus equals 2, right? And, well, what's that going to do? Well, that's going to walk us through. We've used these two. The next step, we'll use these two, and we'll put four, 5 onto our list, right? Now we'll have processed all these guys. We have these guys left. We'll process those, and what'll come out is one mega size list, 1, 2, 4, 5 in sorted order. And you can ignore the fact that I accidentally put that in sorted order anyway. Okay. So at the end, after we've gotten through this while loop, well, we want to, right? So we'll append 1, 2, 4, 5 there, right? So now we'll increment I by 2 again. So it started out at 0, then 2, then 3. By the time it got to 3, the length of the list is 1, 2, 3, 4, 5. I'm sorry, 4. So I would be 0, 2, 4, right? So by the time we get there, right, where there's only one list unprocessed remaining, our I should be equal to 4, and the length of our list should be 1, 2, 3, 4, 5. So we want I to be less than the length of our list of V, or length of lists, and we want to subtract 1 from that, because we're going to stop 1 shy at the end, right? There's going to be that one list at the end that represents everything all of our efforts, all of our dreams, our hopes, our aspirations, well, and the actual sorted list. All right. And then at the end, what we want to do is we want to do this in place, which means that in the end, we want V to have our correct answer. So all we want to do is we want to use some slicing operations to copy the contents of our last list into v, and that should do our sort. Okay, so all this does is it says, don't change where v points, but take all of the elements of v and overwrite them with the contents of our last list, and our last list should be all of the elements in v in sorted order, if we have the algorithm correct. All right. Any questions about the mechanics of this, how this actually works? Because we're going to start looking at how we pull this together again in just a second. And by the way, this is a relatively efficient implementation of this sort.
I have a question.
Sure.
So for when you loop through V, basically append in a list of each item.
You're dropping out on me. What? Yeah.
So you appended each item in V
Right.
into another list inside a list.
Yep.
And for in the while loop, I don't really understand what you're doing in the while loop.
Okay, we'll analyze this and we'll walk through an analysis of this in just a second.
Okay.
Okay, that's what I'm gonna try to diagram this. So let's go over and take a look at what this actually means. Yeah, let's talk about correctness first. We're going to talk about correctness, and then we're going to talk about efficiency. So let's talk about correctness. Oops, and I forgot to turn on the whiteboard. See if this works. Okay, so let's look at what we're doing. So we start out and we create a list. And I'm going to say our original list is 2, 3, 7, 9, 1, 5. Okay, that's 6. That'll be good enough. So we take this, our original list is 2, 3, 7, 9, 1, 5. Okay, we divide this up into individual single length lists. Okay, so we started out with 1, 2, 3, 4, 5, 6 elements. Our new list has 6 elements, but each element is a list of length 1. Okay, so it has 6 lists of length 1. This had 1 list of length 6, right? So now what we're going to do is, during the first step, is we will come down here and we will take these 2 elements, right? And we already have this merge algorithm. And what we said was that the merge algorithm can take 2 sorted lists, right? Any list of length 1 is sorted, and it can return another list of length of the first list plus the length of the second list. So we'll just use merge on this. Let's see. And when we merge those together, we'll get a new list of length 2. That's 2, 3. Right? And this is sorted. That's important to note. And now what we're going to do is we're going to move on to the next 2 values. Right? That's what the I plus equals 2 gives us. And we'll do a merge on that. I need random numbers. But regardless, that'll give us 7, 9. Right? And then we'll merge our last 2 numbers. Right? So we're just walking through our list of lists, taking 2 numbers at a time and merging them together. And this will give us 1, 5. Now, in the meantime, we've added these 2 guys. Right? So now we've walked all the way out to here. We've processed all of our single length lists. And now we're on to processing, right? But as we've done that, we've kind of added these other lists back on. So now we'll process these two lists. And again, we know that we have this this merge property, right? And it can come through and it can give us 2, 3, 7, 9. Right, so now we have one list of length 4. We still have this list of length 2. And so now we select this guy with this guy, right? And that will sort it until we get 1, 5, 1. Because that's what the merge operation does, right? It takes two sorted lists and makes one sorted list with all the elements in it. Okay? And this is our last list. There's no other lists to merge with it. We've now used up all of our values. And that's what we want to return as our sort. Okay, so it's a sorted list. And if you kind of walk through the mechanics of this, you should be able to see that this actually does, what I claim it does. This algorithm actually sorts things. Now I want to add a couple more values onto here because it makes the discussion about, and we'll make this minus 12, minus 17, just to throw a wrinkle in. Okay, and the reason I want to do this is because this is now a power of 2, right? We now have 8 elements. So let's repeat this analysis, and let's see what it looks like with a power of 2. It doesn't have to be a power of 2 for this analysis, for this to work, but it does make understanding what goes on as far as order notation a little bit easier. So now we have minus 12 and minus 17. We add those onto the length of the list, and we're going to proceed the same way. The first step through, because this is a power of 2, this is going to break down very nicely. The first time through, we merge these guys, these single length lists, and we get 2, 3. We merge these single length lists, we get 7, 9. We merge these single length lists, and we get 1, 5. And we merge these single length lists, and we get minus 17, minus 12. And you notice that I threw a wrench in there so that things wouldn't be completely in order. And as we generate each one of these, we pop them onto the end of the lists so that they're sitting out here. We've now gone through and we've consumed all of the lists up to here. But now our new list, in the meantime, has gained 4 new lists of size 2. We'll come down and we'll do our merging here as well. This will give us 2, 3, 7, 9. Right? Our merge can walk through and give us a double-sized list, all in sorted order. And then we'll merge these 2 lists, and we'll have minus 17, minus 12, 1, 5. Well, we've added these 2 on. We've now consumed up through here. We've added these two guys on. So all we have left is we have these 2 lists of length 4. We'll come through and we will merge those together. And we will have minus 17, minus 12, 1, 2, 3, 5, 7, and 9. Okay? Now, here's the interesting part. To generate all the lists of length 1, it took us 1, 2, 3, 4, 5, 6, 7, 8, right? Because we had to take each one of these elements, turn it into a list, and append it onto our lists array. Right? So the work here is 8, right? We had to do 8 things, and the size of the list is 8. So that's order of n. Then we had to generate 4 lists of length 2. Well, I said our merge routine, right, takes, if you provide it with an L1 and an L2, I'm sorry, an L1 and an L2, the work required to merge 2 lists of length 1 is about 2, right? It's proportional to the size of both lists. And the key is that to generate this takes 2 operations, proportional to 2 operations. This takes proportional to 2 operations. So to generate both of these takes 4, 6, and 8. So the work in this stage is again about 8, or order of n. Merging 2 lists of length 4 takes about 4. Or two lists of length 2 takes about 4. We have to do that twice. Again, the work to generate this entire stage is about order of n. And then to generate 1 list of length 8 from 2 lists of length 4 is again about 8, which is order of n. So to generate each one of these stages that I called out is about an order of n operation. So now if we want to know the running time of this algorithm, what we need to look at is how many stages we have to go through. Well, for 8, right, we had 4 stages, which is 3 merging stages plus 1 prep stage. We were generating those lists. If we just had a list of length 4, right, if we wanted to stop here, let's say we only had these first 4 elements, well, then it would take us 3 stages. So this is for 8, takes 4 stages, 3 merges and a prep. For 4, it takes 3 stages, which is 2 merges and a prep. And actually, if we wanted to do 16, right, if we had a double size list, we would just have another list of length 8 over here, and we would take 1 more stage. So for 16, it would be 5 stages, equals 4 merges plus 1 prep. So as we double the number of elements in our array that needs to be sorted, we only have to add 1 stage, right? And in fact, if we look just at the number of merges, right, this is constant, or this is order of n, right? If we look just at this, at the number of merges, well, 16 is 2 to the 4th, 8 is 2 cubed, 4 is 2 squared. 2 squared. So this is order of log n. So we have order of n cost per stage, order of log n stages, so this is order of n log n. And if we want to include the prep time in there, then it would be plus and another order of n, right? Because there's only one prep stage. It also takes n to calculate. But again, because of the way we do order notation, having arrived at this n log n is bigger than n. So we would just drop that order of n analysis. So analytically, what we're seeing is that in order to sort a list of length n using a merge sort, right, what we're actually seeing is that this merge sort, the merge stage, where we're merging all of the lists of length, n over something together into a larger list, that takes order of n to do the entirety of the list, right? There's only n elements in the list. Each element gets touched only once. And we can do it in log n stages. Okay, and here's the question. What if it's a list with an odd number of items? Turns out it doesn't matter. This is an upper bound. There's somebody here that said you could add a 0 to the list to make an even number of items, go through the whole process, and then remove the zeros. Yeah, you could do that, but it turns out it doesn't really matter, because all that ends up happening is what happened the first time when I had 6, right? You end up merging a length 2 list with a length 4 list in the final stage, or you end so you end up with a power, 2 versus 4, 4 versus 8. You get a mismatch there, but it doesn't change the asymptotic behavior of the algorithm. So we always analyze it in terms of a power of 2, and that's an upper bound on anything from the previous power of 2 up until that value. And so the question is, wouldn't it be n log n? Why would it be n log n? Isn't log 10 kind of arbitrary? Didn't actually show up there. So there's a constant, right? You can change between logs by multiplying by a constant. Constants are discarded. We just say order of n log n. We don't actually specify the base. It doesn't matter whether it's log base 3 or log base 2. There's just a constant factor that figures in. So yeah, you're right. And in fact, the analysis I did was in order was in base 2. But once you get it into the log realm, where multiplying the length of your input by any constant, gives you, if you're in log base 10, you multiply by 10 and you show that you get one more stage, or a sublinear number of stages. Okay, so it just once you get into the logs, and by the way, again, this is log is we're not specifying the base. Does that make sense? Right. And since it's a plus, by the way, since it's order of n plus n log n, that lower constant, you discard all lower order terms when you're doing order notation, because as the input gets larger, lower order terms become their contribution to the overall time sum goes to 0. Okay, let's see. And where else am I? Have I caught up? The merge sort function is order of n log n. The merge function is order of n in the size of its inputs. And you don't have to make sure it's, and so there's a question, why would the third merger only require 4 comparisons per list? Wouldn't you need more to make sure it's ordered? No, that's the beauty of the merge algorithm. If you start out with ordered lists, there's only one comparison needed to extend the size of the ordered list of the new double-sized list by 1. So you don't have to go back through. And even if you did have to go back through, that would still only be an additional n. So it would be 2n instead of 1n. And again, the higher order terms just get discarded. The constants just get discarded. All right. All right, I'm going to, where do I want to go from here? Let's go back to the